Our third talk today is by Emmanuel Fleurantin, and he's gonna tell us about computer-assisted proofs of attracting invariant tori for ODEs. So take it away.
Okay, again, thank you for having me here. In this work, we will study existence and regularity questions for attracting invariant tori in three-dimensional dissipative systems of ODEs. Our applications, we'll consider today only the resonant tori, although we also have a proof of a rotational tori. Okay, so let's get started. So a little bit of background. We initially looked at this vector field, which is the Langford system, where we have those parameters, and then we consider alpha as our bifurcation parameter. What we did is, in order to find periodic solutions, we had to set a Poincare section. So we pick x equals 0 to be our Poincare section, and we fix only for positive y's. And what we notice is for alpha with between 0 and 0.65, we have an attracting fixed point. Okay, and then continuing continuing the bifurcation, changing alpha again, we notice that we have a Neymark-Sacker bifurcation at approximately this number, where the fixed point loses stability. So a supercritical Neymark-Sacker bifurcation. Okay, so what we have here in the first picture, this is for alpha, which is 0.75. We have an attracting limit cycle that you see here. And of course, on this side, what we see here, we see a plot of the half torus, where in the black, you have components of the torus and intersecting our Poincare section. And in this case, it's x equals 0. Next, this is alpha, which is about 0.81. What we notice is, okay, so these blue dots are saddle cycles. By cycle, we mean if we take this fixed point here, we iterate it, we get here, and iterate it 3 times, we get back to the original one. And the green one that you can't see clearly here are stable cycles. Well, the interesting behavior is the blue here is the unstable manifold of the Seidel cycle. On one end, the unstable manifold of the Seidel cycle wraps around the stable cycle, and on the other end, it wraps around the limit cycle. And over here, in between this picture and this picture, we have homoclinic tangencies that gives you another special case that we didn't examine into very detail. But after that happens, we have the saddle cycle collides on the limit cycle, and then we have both ends of the unstable manifold wrapping around the stable cycle. Okay, so in the proof that we're going to show you today will validate this resonant tori that we see here in phase space. And we call it resonant because it's the union of the blue stable periodic orbit, the green saddle periodic orbit, and the unstable manifold of the saddle periodic orbit. Okay, some remarks. These tori, they are hard to analyze using functional analytic techniques, as they are not globally smooth. Okay, they are only C0. So Fourier approximation would decay really slow if it converges at all. So what we're doing here is we're using topological methods that we assume that will be best here. So these are the methods that we're going to use. The first thing that we'll talk about, we use this lemma, which is a variant of the mean value theorem. We say let F from Rn to Rn be C1, and let B for a subset of Rn be a Cartesian product of closed interval in Rn, and let P1, P2, and B. We could choose, then we could choose an n by n matrix A in the interval enclosure of DFB, for which we'll have f of P1 minus f of P2 is equal to A times P1 minus P2. Of course, the matrix A depends on P1 and P2. Next, we'll use a famous theorem. This is from we took it from a paper from G. Ahlefeldt in 1994. This is the famous interval Newton theorem. So we say let f from Rn to Rn be a C1 function, and let B be a Cartesian product of closed intervals in Rn. If the interval enclosure of DFB is invertible, and there exists an x0 in B such that the x0 minus the interval enclosure of DFB inverse time f of x0 is a subset of B, then of course there exists a unique point x bar in B, x star in B such that f of x star is 0. Next, we'll give you a definition of what we call a k-dimensional Lipschitz manifold. So this is, we have a k-dimensional Lipschitz manifold, a k-dimensional manifold subscript m in Rn. if Lipschitz, if for any point P in M, there exists an open neighborhood U of P in Rn, and an open set B in Rn, and a C1 diffeomorphism that's a gamma that sends B to U, such that M intersection U is a subset of gamma U of the cone attached to gamma U inverse Q intersecting B. Okay, so in this picture here, we have the cone attached to gamma U inverse of Q, where the white region is the cone. And here we have an example of a Lipschitz manifold. And in our case, we have, since we're looking at two-dimensional tori, K is 2 and N is equal to 3. Okay, so in our next application, in our next methods, we'll show we need to do a few things. We need to establish an attracting neighborhood for which the trajectories converge to a stable focus that we have. We need to establish a bound on the unstable manifold of the hyperbolic fixed point. And finally, we need to propagate the unstable manifold by our map. So here we show you, well, this is something that's known, but how to establish a attracting fixed point. We say let F from Rn to Rn be C1, and we pick a constant lambda in this ball, in 0, 1. Let B be a Cartesian product of closed interval in Rn, and which is an n-dimensional cube. If F maps B to itself, and for any A in the interval closure of DFB, we have the matrix lambda identity minus A transpose A is strictly positive definite, then there exists a contracting fixed point F in B. Okay. Here, in order to validate unstable manifold, we need to establish cone conditions. So we pick a constant L, and this is how we define our cone attached to P. So we break P here is in the hyperbolic fixed point, so we have to break it in unstable and stable eigenspaces and pick those directions respectively. And then how we establish unstable manifolds is we first assume that for any P1 and P2 and B, such that P2 is in the cone attached to P1, we have, if we have f of P2 is in the cone to f of P1, so now we pick a constant M, we let it be a fixed number, and we assume that for any P in the cone attached to a P star, here will be a hyperbolic fixed point, intersection B without P star. We have the following inequality. So then what we have the unstable manifold of P star is contained in the cone attached to P star. Of course, there is this horizontal disk WU that says BU to B, which is the graph of W. Okay, so now what we're going to do is we're going to try to propagate. So what we'll do is we say that this is our theorem, let's F from Rn to Rn be C1, and we have D1, B2 in a subset of Rn. In this case, P1 star will be our stable fixed point, and P2 star will be hyperbolic. And then if there exists an n greater than 0 and an x in BU, such that any P in our unstable in BU, which is inside our unstable, the cone attached to our hyperbolic fixed point, if we iterate it under our map n and it get caught in the basin of attraction of our fixed point, then there exists a contracting fixed point P1 star in B1 and a heteroclinic orbit from P1 star to P2 star. And in all our cases, F will be the Poincare map. Okay, so here, if there exists an n greater than 0 and an interval I subset of BU and an x star in I, such that any P in I that's in our cone attached to P star, if we apply the map in the unstable correction and stable direction, it maps back to I. And if we iterate it and it gets caught in the basin of attraction of P1, then there exists a continuous curve invariant under F, which joins P1 star to P2 star. Okay, so now we have established those. So now we will look at our vector field, and we let phi t, which denotes the flow of our vector field. So then all we have to do here is to establish that we have a resonant tori in phase space. So we assume that we have P1 star, which is a contracting k-periodic orbit of a Poincare map P, and P2 star, which is a hyperbolic k-periodic orbit of B. So we have established that the invariant curve gamma will join P1 star to P2 star. And all we have to do is integrate it under the flow to get our two-dimensional torus, which is invariant. Okay, so next we'll talk about our validation techniques, what we use to validate the resonant tori in the Langford system. So, okay, some remarks. To run our proof, we had to use the CAPD library. So this is the reference here, and we'll show you the reference later. But in order to validate the fixed points, we consider a map from R2 to R2. And in our case, we consider the Poincare section x equals 0. So it takes 6 iterates of the Poincare map to get the point back, the fixed point back to itself. Okay. First, we have P1 star, which is our stable point, fixed point, and P2 star, which is hyperbolic. And then this is P1 star, of course, this is a stable cycle. P2 star is in the hyperbolic cycle. And then we define G such in this manner, such that GQ1, Q6 is equal to 0. And then what we do here is we use the interval Newton method to validate that P1 star is in this enclosure and P2 star is in this enclosure. And then we pick two matrices A1 and A2. The choices of A1 and A2, we pick them such that they put the derivative of F1 and F2, which are local maps around P1 and P2 star, in approximate, well, first we have to shift P1 star and P2 star to 0 in their local coordinates, right? Then we pick F1 and F2, which are local maps around P1 star and P2 star respectively. And A1 and A2, we pick them such that they put the derivative of F1 and F2 at 0 in approximate Jordan form. And then this is how we define the local map. Okay, so we pick B1 and B2 to be those enclosures, and the choice of B1 is because we need to establish bounds on DF1 and DF2, and we use those bounds to validate cone conditions. So picking our L to be 2 times 10 to the negative 4, and then finally picking X bar to be this value. We validated that we showed that the unstable F2 maps I to itself. And then picking n equals 25, we propagate the set around inside the unstable cone, and then we have that it gets caught in the basin of attraction of our fixed point. Okay, and then this by theorem 7 established the existence of an invariant curve of f, which joins P1 star to P2 star, and of course we get the resonant tori by simply integrating that curve under the flow. Okay, so we had a few problems. Well, we had a problem validating the CK tori for smaller parameters, okay? For example, for alpha, which is 0.75, we had some problems. The problem here is because there are some regions that we have uniform, you have strong contraction and we have expansion also, right? So, and what we do is once we look at this section on our Poincare curve, on our Poincare, when we look at the star-shaped curve on our Poincare section, right? We had to enclose it with boxes, and with the union of those boxes, we call it U. And so we had to break those boxes into 10,000 cubes. And then we were able to show that F maps U to itself, but such validations were very, very time consuming, right? But we also need to validate cone conditions. And it's very hard because, you know, it's, as far as like the computer, because our map consists of 16 iterates of P, and it was very hard to show that to validate those cone conditions. So what we say is like our method is is good, it works if your star-shaped curves is uniformly contracting, but if it's not, then we have a problem. Okay, so this concludes my talk. I mean, I know we have more, I would have more to show because there's also a case where we considered a rotational tori, but I was, due to the time limitation, I'm not able to show it, and these are our references. So I thank you for the time.
Thank you very much. Thanks for your nice talk. Are there any questions?
Hello, this is Alexander Czechowski. Very nice talk. Can I have a question?
Of course.
Yes, or question or maybe a suggestion, because I was also working with this type of integrators for this problems where you don't have strong contraction, but you may have some expansion, and so one of the problems that you had was that you had to subdivide the domain in many boxes.
Yes.
So did you try to parallelize it perhaps? Perhaps this would be a good idea, right?
Well, yeah, I mean, the problem here is like, because we also had some twist, right? So when we when we did the iterations, we didn't have some boxes went back in, but some of them kind of went back out. So because of the twist, the strong twist in our example, it didn't work quite so well. Even if we just subdivide the boxes into smaller boxes to see what's going on.
I see. So perhaps another idea that I used at some point, but you could also try intermediate sections.
Okay.
Then to control this wrapping effects more. Then you adapt your coordinate system at each intermediate section to factor out this twist.
Okay.
So it could, I don't know. I don't know that your problem that well, but just throwing it out there.
Okay.
Thanks.
No
Yeah,
problem.
that's a good suggestion.
Thanks, Alexander. Are there any other questions? I have a question. So you say you have another problem, right? That you can also solve.
Yes.
Is that harder or is it easier? And so can you say a little bit about it?
Yeah, it's easier because we have uniform contraction. So we consider the Vanderpool system, and then we have periodic forcing. And then in the Vanderpool system, the regular Vanderpool system, we have an attracting periodic orbit. And then once we add those perturbations, and then it gives you the rotational tori and phase space. But this one, we had uniform contraction. So it was easier to validate using our method than the one that we have right now. And we also were able to establish regularity. And for some parameter values, we got to C9, although these are not sharp estimates. I mean, this is the most we could do. It could be even smoother. But in our case, we could only establish C0.
Okay.
For the resonant tori.
For the resonant tori, correct.
Any other people with questions?
Yeah, well, can I have a question?
Of course.
Yes, this is Kanabe Matsui from Kyushu University in Japan. Thank you very much for a very interesting talk. And my question is the smoothness of validated manifolds. In your method, could you validate the C0 or Lipschitz smoothness of manifold?
So we only were able to, in the resonant tori, we were only able to validate C0. Our torus is not even Lipschitz because we have rotations around our stable fixed point. So we are only able to validate C0.
All right.
But because it is only C0, we can't validate C1 because the thing is not C1 at all. It's only.
Well, yeah. Okay.
How about C1 smoothness? I mean, using the rate conditions, some more regular version of cone conditions can provide C1 or CK smoothness of manifolds. But have you tried such kinds of conditions?
Yeah, we tried rate conditions where we look at lower bounds and upper bounds in the we tried that, but it didn't work for the resonant tori. It only worked for the rotational tori.
Okay. Is it because of some kinds of resonance?
Yeah, it is. It is, of course, because of the resonance.
Yes. All right. Thank you so much.
Thank you.